This one's good. But look around. Is there any way to make it become more stable? What type shape?
1-2
Hydra shape. 1-2 hydra shape.
Hybrid. So H.
H jump. Show the H and jump.
Right.
Show the H and the arrow.
Oh.
Okay. Okay, good. So this one we call rearrangement. I think half of you forget. Did you forget, Frank? Anyone remember about rearrangement before I remind you? I love you, Kaka. Wendy too? I love you too.
There is 1-2 hydra shift in chapter 7.
Okay, good. So, in order to synthesize alcohol from alkene, you can just add acid and water. But what's the issues? There are two issues. First of all, it must follow Markovnikov rule. It means OH1 attack to the more substituted carbon. And second, rearrangement. Right? Good? -1. Positive charge.
I was going to do it.
Okay, so this is really good, but when you form the rearrangement, when you form carbocation, check for rearrangement. Are you caught? Who that? Frank?
No?
Oh. Okay, good. But now, good job, Andre. Quick. So in the future, you can just done. Because in exam they will ask what's your product. But if you forget, you can follow this one, right? Okay, now, but in the lab, I want to synthesize something else. And sometimes I want to avoid rearrangement. What happens if I want to just synthesize this one? What happens if I want to synthesize this one? It's become issue, right? So the first way we can do is, we call this OC maturation. OC maturation. So the reagent have two steps. The first one is, Frank, mercury acetate. So you can think like this. The first one like this, with water. And the second one is, this one you need to memorize, I'm so sorry. A reducing condition, a reducing reagent, NaPH4. Okay, now let's look at the mechanisms. Now, stand with me. First of all, this one is an transient metal. They're really complicated and they have empty orbital, empty d orbital, so they can receive the electron. And at the same time, it's like bromine, it also has electron, so they can give back to the ring, to the alkene, and kick this one out. Does it look familiar? And do you know what does it form? Mercurium ions. Oops. So again, mercury receive electron, give electron back, and break the bond between OAC. Do you know what is structure of OAC? Acetylene group. Acetylene. But I don't want to draw everything out here. Okay. Everyone agree? What next? 2 plus?
It's Ag plus, so
Oh, this one Ag plus already?
on your right.
So let me look at it. The one on the right, this one?
Yeah, well, one of the bond needs to fall, so it's going to be.
This one 2 plus?
No, one of the bond needs to fall into the Ag
What do you mean?
And then we need to split the cycle if you have to, and then add the water.
Oh, wait. So this one first, right? You agree this one? Okay, what is the next step?
Yes.
Again, I am a positive, I will have ring, I will attract electron, right? Between these two, where water will attack to? Where? Left. Because? Secondary. Okay, come here. See? Just asking yourself, this how I study organic chemistry. This one is AgOIC, right? This one is O plus. Again, what happens next with this one? I need to neutralize it, right? By what? Maybe OAC, a base, anything. And then after first reaction, I will have this structure. See? And the next step, oh, this is not what I want. I want this one, right? But in here, I have an HEOAC. I need to add a reducing condition. You know why? BH minus, pH4 minus. They can give away an hydride. They can give away a hydride ion and kick this one out. So this one is actually this one equal with. Don't worry. This one equal with. They will come here, replace He mercury, and kick mercury out. Done. Good. How is it? So when you see this one, what's the first step? Form the mercury ion, right? Next one, nucleophile attack it. If nucleophile is water, you will form alcohol, OH. If nucleophile is alcohol, you will form what's functional group? Ether. Okay. Something stupid there. Okay, the question 10 in your exam is wrong. I write wrong. So now I will make enough for you. I will choose for you a reaction I really love and see how you do with it. Okay, mechanism done, right? Okay. Okay, now add this one into your booklet. Show me the mechanism of the following reaction. Okay, predict. Actually, in the problem, they give you the product and propose mechanism. But I want you to show me the mechanism and show me the product. now form the ring structure for me. First of all, I give away to mercury. Mercury give it another one for me. And I need to break one of them. Okay, and the structure for me is what do you mean? It's just a catalyst. Not really, not really. So you have a carbon here, right? Okay. The thing you just do, you form a ring with. See?
Oh.
I form a bond with Hg, right? Hg form a bond with me. And then?
And there is.
Okay. What next step? Okay. So now I form the intermediate. Now I need to find a nucleophile to attack me. Good. And most of you now love the magnesium ion, but what's the next step? Oh my God, where's my water? It's supposed to have a water, but I don't see it here. So what is the product? And you see this one is the third time. Correct, but you are losing. You lost one carbon. Oh no, you are right. You are right. Perfect. Good. Good job. Good job. Wait. You need to. You just do a base, right? What base you have? No, this one is in the second step. One base you have is acetine group. BH4, actually that's a really strong precipitate reagent. Then we donate a hydride ion. And this hydride ion will replace or substitute. So this whole group is replaced by a hydrogen. The chart because something like this. And actually this one can be activated. Okay, Wendy, show the mechanisms. Where is my oxygen from here? This oxygen, right? Okay. Keep going. Aston, you done? Good. Not attacking at all. You attack here. Oh, yeah. You have this one, good. First of all, we need to neutralize this one first. Neutralize.
Why this can why can I use
NaBH4 is a releasing condition. And when you have number one and number two, it's mean number one finish, and then number two. So it's moved from this one after the first one. Okay?
Yeah.
After the first step. And then second step to give your product. Yes. Yeah. Perfect. Joey, how are you doing? Right, again, this message, we talk a lot today. And then after you form the magnesium ions, the next step is, where's my nucleophile? Do I have water here? Oh, in my reaction, I don't see water. But come on, look at your molecules. You have a nucleophile inside your molecules. This we call intramolecular reaction, and this always favor. Okay? And actually, no, not that one, but the hydrogen. Not a lone pair, but the whole hydrogen atoms. Eunice, how is it? Okay, your turn to explain it, let me. Make sure everyone understands.
First, break the double bond and
Oh, yeah.
so form this form.
And
And then there is electrons in oxygen, so the electron will go to the tertiary carbon, and there it can bear 5 bonds, so the bond break to the atom, and then form this structure, and then the electron goes to the oxygen and break the bond. Then there is
wrong. The pair of electrons should go to. Is it going to? Is it's going to neutralize. So it's go to hydrogen. And the bond between O and H is broken, and that pair of electrons go to oxygen. So 9 over 10.
so it's minus.
And okay, good. So Eunice, after we form something wrong here. After we form the iron, the next question you ask is, what can attack it, right? How can I release it? And looking around, do I have any nucleophile? Look first, inside the molecules, do you have any nucleophile? If no, look around, what is the most abundant nucleophile? So check inside the molecule first, and then check the environment. And this is nucleophile, right? They will attack to the tertiary, your experiment ready. Because this positive charge will be more stable. Attack here, form an OH, oh, positive, right? I need to neutralize it. And acetylene group will grab the proton and neutralize to form this one. So this one is your product after the first step. And the second step, when you add the reducing reagent, this one they will donate a proton to replace the mercury group. Okay? Good? This is really challenging question. But you managed to make it. Okay, good. We will come back to this reaction later. Now move on. Now my question become crazier. This one look familiar, right? This look like bromonium ions. Does it look like? Kind of, right? But now my question, can I erase it? Now my question is, from this one, I want to form this one. So the first one, when you add acid and water, or when you add mercurium, oxymercurium, right? These follow what rule? Markovnikov rule. So OH will go to more stable carbocation. But here, I want to make the OH group in the least substituted group, or the carbon with the most hydrogen. I need to use another reagent. Do you understand why we need a new reaction? The first reaction, they have rearrangement. If we want to prevent rearrangement, we use oxymercuration. But those only form OH group in the high order carbon. If I want to form it in the low order carbon, I need to use hydroporation. So the first one is BH3, THF. I will talk about this one, BH3. And then the second one, you need to memorize it. H2O2, OH minus, water. So it's happened in a base reaction. So now let's talk together. Actually, I give the explanation in the handout, but I will explain it for you. Okay, now this one, look at your handouts. This will be the easiest way. I have this alkene group. Okay. And now when I add BH3, actually BH3 is really special. They are happy, they have 6 electrons, but they also have an empty B orbital. So it can accept electron, right? So this one is also an electrophile. Agree? And then BH3 can come they can approach the molecules in 2 ways. This way or this way. You think the left one or the right one is more stable? Chuck? Aston? The left one or the right one? Which one is more stable? So BH3 have a 2 way to orient to the one. They can come like this, or they can come like this. Which one is more stable, Aston? Left or right? Why left? Eunice? Why do you think the left one is more stable or more feasible? Andre?
There's less steric
Steric hindrance. The bond is huge. And look at this way. This one has a CH3 group, so a lot of steric hindrance. So the B will refer to form the less substituted carbon, right? Less steric hindrance. And in here, there's something weird. Look at it one, it's not magic, but in order to do it, you need to read textbook. I told you this one have free B orbital, right? This one will get electron. Okay? But this one become negative, and it can actually donate the hydrogen into the other carbon. Get it? And the thing I have will be hydrogen, BH2. Do you see something special? What is type of this addition? Syn addition, because they add on from the same side. D2 reaction happen at the same time. Okay? How about the oxymacration? Syn or anti? Anti, right? Again, I didn't mention about it. But the ring of the mercury ion, the water must attack from your back.
What was that term that you used for the BH2 THF? Like after oxymercurization, there was something.
Oxymacration?
After that,
Hydroporation.
hydroporation.
Is it? Borohydration. Borohydration. So this method we call borohydration. Okay? And then the next step is you need to remove this one, BH2, right? And replace it with OH group. And you don't need to know the mechanism for this one. Just add beta side and base. Done. This group will replace a BH2. And you will have okay. Be careful with the stereochemistry because syn addition. But actually this one also have another isomer that is. But remember, D2 group always in opposite direction. This group and this group always in opposite direction. Do you know why? Because OH and H must be same side. Agree? Okay, now move on. Do we have any problem for this question? Okay, now question 11. Predict the product of the following alkene addition reaction H2O by hydroporation, oxidation. Okay, this question will for Phoebe and Anne. So, rule of thumb, when you see pH3 and THF, H2O2 and OH, OH will give into the antimaconical, right? To the less substituted carbon. Okay. And I require you to remember the reagent. You need to memorize it. This is a 9 thing. Okay, Phoebe, this one, and this one, go. So when you use the hydroporation, the OH group put into the less substituted carbon. With the other two ways, they will add to the more substituted carbon. So this one, antimaconical. Phoebe, go, go, go. And come. And come. No, you need to come. Okay, so what's in the first reagent? You need to memorize the reagent first. Come, I will help you, don't worry. So the first reagent you need to use is pH3, right? Go and go. Okay. And the second step, second step you only need a peroxide, H2O2, and basic condition. So this reaction will add the OH group into the less substituted carbon. So the carbon with the less steric hindrance, right? So now look at this one, where the OH will add to. When I have this carbon here and this carbon here, which one will add? But this one has 1, 2, 3 substituted. This one has 2. So the OH group will prefer to be on. But for the other mechanisms, right? When you use mercury, or you can use, this will add here. But for this one, they will do the opposite. Okay. For your. Okay, good. Just show me the product. Just show me the product, don't worry. And this is actually not a mechanism. If you want a 100%, look at the mechanism of this reaction. I don't think it appears anytime. They will just ask you to provide the reagent. But remember, this reaction is to make the OH group antimaconical. And another thing is, this must be C addition. So OH group and H must be same sign. With oxymacration, this is anti-addition. With halogenation, when you add with Br. Good. Halohydration, anti, right? Whenever you see the ring, always serotonin, go to the back. With this one, when you add an OH, right? Okay, good job. Phoebe? Good job. So I just want to emphasize this one will add OH into a small one. Good job. So everyone, look at the left one first. This one is so easy. But you will lose a mark because you don't remember the reagent. And the next one, you will lose a mark because you don't care about stereochemistry. In here, I add OH into one group and hydrogen into the other group. And these two groups must be same size. Why do I still have double bond? Okay? Good. Good job. The same. Okay, now are you done? I will have a quick test for you. Not now. Can you look at the handout I give you today? Look at question number 2. Raise your hand. Oh. Anyone? How we can make exam? We're so behind. Please provide the reagent for Okay, I have 3 reactions by adding an OH group, but to different position. Now tell me what reagent you use. If you do this question correctly, you're done. I'm not done in that way. Tell me what reagent you use. First of all, what reagent you use for this one? A. How many steps? UBA3. Look at this one. I want to add OH group into the less substituted carbon, right? I need to use antimacronical, so BA3, THF is solvent. Just write if you. The second step will be
H2O2.
and okay, keep going. How can I form this one? From here to here. Oxymigration. The first reagent will be mercury acetate, right? Second step. One more.
THF.
Water. You need water to add to here, right?
THF work as well, right?
THF is just a solvent. Water attack into formation. Second step, NaBH4. How can I form this one? It looks so weird. My double bond is there, but my hydrogen OH group is here. What do I use? H plus and H2O. Okay, now big picture, hydration. It depends on where you want to put it. You can use different reaction. Good.
Question: why will we need to use this in the future?
Huh?
Why are we doing just
What do you mean?
like?
So it depends on where you want to add your OH. You need to use different reagents. Good. Okay, next reaction, hydrogenation. We're almost done, don't worry. The first two is the most difficult one. Done? Okay, keep going. And you will have a 6 to 8 mark related to this question for sure. They will give you different reagent as for the product. Oh my god. Okay, from now on, let's memorize. We won't go to the mechanism that much anymore. The next one is hydrogenation. Okay. And you just heat the alkene with hydrogen. And what's the product? the product is an alkane, right? So you just add 2 hydrogen into 2 sides of double bond. Okay? However, tell me about addition. Is it syn or anti? Syn or anti? Why syn? Okay, now talk about mechanism a little bit. So in here we have catalyst, right? Catalyst are metal, and they provide hydrogen on the surface. And when your alkene come here, D2 is not like this. How go? Okay. D2 hydrogen will transfer on the same surface. So that's why syn addition. Okay, test question. Provide the product of this reaction. Hydrogenation. Hydrogen and catalyst. Catalyst is a metal with the atom of hydrogen can attach to it. Oh my god, it's in the thing already. Skip, skip. But you see, right? What's the product of this one? Cis, right? Because 2 hydrogen on the same size. Hydrogen, hydrogen. They add to the same side. So you must care about this one. Keep going. Oh, damn. Next question, question number 12. Ha ha ha. The crazy ring. So during the weekly class, I just repeated. During this weekly class, I discussed a basic thing. For exam reviewing, I will just do exam questions. And it's really hard, right? So I will review the material theory just a little bit. For anyone not coming, I just review a little bit, but I will focus on the challenging material. Anyone want to show me the product? Remember, in this reaction, the molecules must approach the hydrogen attached to the catalyst, and then the hydrogen is transferred to the alkene. I don't want to show the mechanism. So it transfer, for example, here. So what's the product of this reaction? Think. Why I even ask when I talked just about a few seconds ago. What's special about these molecules? This molecule, actually, I can rewrite structure like this. Okay? So it's made a ring, right? With another smaller ring on top of it. Eunice, any idea? What do you think? So, what is the purpose of this reaction? H2BDC. To add hydrogen, right? Okay. It should be easy. But add to where?
No answer bubble.
Huh?
There should be a below the
Show me. Okay, just can you rewrite it? So what is your final product? Just show me. Actually, I should make it a little bit more complicated. Okay.
So basically, you should add like the loaded plane because if it were to stand on the
Oh,
metal catalyst surface, it would be standing like this or two.
okay, good.
But if we stand like this, and so hydrogen would add from that side, it would be there. Basically, it would be like this. H here and that H.
Do you understand why?
Yeah. Because basically, like when the reaction happens, you have the catalyst surface, which is this. It the carbon, the alkenes, it stands in its double bond. So imagine this standing here. So like visualize in head, this would be where you tilt this towards the right. And so if only the H could only go from behind because there's no space in the front, obviously. And it's also easier.
Okay, I understand you. Anyone else understand?
It's hard to like.
Okay, so think like this. You have a ring, right? You have a ring. And the top one is really gravity, static ring. The lower one is free. So which phase will approach to the catalyst? The bottom one or the top one? The bottom one. So hydrogen will be transferred to the bottom one. That's my point. Why understand mechanism can help you to navigate in the weird case. Okay? Okay, next question. And another characteristic of this reaction is because these are catalysts, so they are really, really specific. Not just really. They just add to alkene. They don't add to other carbonyl group or nitride group. So next reaction. Okay, I have this one. What the heck? Here. What's my product? There are two double bonds, right? Which double bond we will react?
Yeah.
Just this one. And the final product will be? Ta-da! Done, right? My main point is they just react with alkene or alkyne. Okay, next reaction. Kaka, come here. Run me the product. Just the product. I don't need to you run the question. Vivian, next question. Run me the product. Oh my God. Yeah, just show me the product. Okay, good job. Are you done? Are you sure? It looks weird. Where's my benzene ring? Again, benzene ring, they don't react with A2PDC at a normal room temperature. They will react at I think 600 degrees, but not at room temperature. Okay, done. Good job. So in here I have two other double bond, two other type. The double bond in benzene ring and the double bond in carbonyl group, but they just attack to this one. Again, I have nitride group, but it attack only the bond between CC. Specific? Good, good? Move on. The next one will be challenging.
Like this attack on the CC itself.
Because this catalyst has some kind of specificity. Specificity. Yeah, of the catalyst. So it's specific. It attacks alkene group. Okay. I want to go to the mechanism of this reaction, but maybe next time that we just look at the oxidation of alkene. Okay. Now sometimes you need to form some other structure. The addition of the hydrogen, right? We call that a reduction. And sometimes we will have oxidation. What does it mean? When you have alkene group and you have better-side carboxylic acid, so this means usually you can see the structure like this, CO3H. Does it look weird?
Yeah.
Because the structure is like this. Okay. So this is better side, and as I said in the beginning, this one is really strong oxidizing reagent. So the mechanisms, I want to say it. So the mechanism is, this one is strong oxidizing, so they will get an electron from double bond, but at the same time, they need to give back electron to form a ring, right? You see? And then the bond between these two must be broken because this one cannot form more than 3. And that's why I don't want to mention it. And this one here, give to this hydrogen here, and this one go to here. That's why I don't want to start. And but the final product is alkoxide group. So please review the mechanism by yourself. I will post some questions on the Google chat group to test your understanding. But my strong main idea is when you got this structure, CO3H, you will form alkoxide. Good? Good. I know, it's crazy. So the first one also take an electron, but it needs to give back, but it cannot accommodate more than 3. So the bond between O and O must break, and to come here, and then this triple bond here come to grab the H here. And then alkoxide. You can follow the arrow and you will see. And this is concerted reaction. Everything happens at the same time. But my point is, from this alkene, after CO3H, I got alkoxide. This is I want you to know for now. Done. Okay? Now, I want to ask you. What is the product of this reaction? The question is why? Why do we even need alkoxide, right? Why we need to display structure? Because this is really reactive species. You know why it's reactive?
Angle strength.
First, angle strength. So they want to open it. Second, this one is right? So these two sides are really reactive. Okay, now just show me your reaction. Okay, what's your product? Anyone? What the first step will happen? Aston? To H plus. Good. Right? Okay, what happened next? Everyone, what do you understand why Aston proposed this one? And what happened next? Huh? Bond break? But wait a little bit. Why it can break? Which one attack? It will attack to where? Okay, secondary here. What attack from which direction? In this case? Bottom one. So you will have and right? So this is just one example. You will see it again for sure. Next reaction. Oh, I know someone is. Question 13. Try to think. This is a break for you. Question 13. This is another way to form alkoxide, but how? How can you do it? Luckily, I don't need to read all of these things in the exam reviewing session, right? It will take forever to read all of this. Someone is doing right. Someone is looking at his own notes and format already. Good job. Okay. First reaction looks so familiar, right? Halo hydration. I forgot to bring the point. Why always attack there? Where the attack? Here. No. What's the product of the first reaction? Oh, Scott, I'm crying inside. I'm crying. Look at the okay, good. Okay, Ariel, can you show me the product of the first reaction? So that's why you just lost about 4 marks in your real exams. Look at the solvent. Wow, kimbap. Where did you buy kimbap?
Nearby store.
Nearby store. Which one?
The one on the Bay Street.
Oh. How is it finished? Okay, good. But how from this one to this one? Which one? How we have OH here? Okay. And it attacked to? Okay. First of all, it's from here. OH. Okay, good. So this is a reaction you never see before, right? No, the first one you never see before. No, okay, this one better. But somehow from this one to this one. How? Almost everyone, we are almost done. Just stand with me for a little bit more. Okay, look at your solvent, right? Okay, but this is your first square. But now when I add NaOH, and what? H2O? Okay. Actually, just NaOH is enough. And I have this structure. How? Any ideas, friend? Huh?
You have two OH groups.
Not quite. But under this condition, if you want to have that condensed reaction, this happens at really high temperature. You know how we can from this one to this one? Okay, what OH can do? OH is a base, right? It can deprotonate. So, this is another way to synthesize epoxide, right? This one come here and become right? Any idea? What happened next?
OH combine.
This, right?
Yeah.
Come here,
Yeah.
kick this one out.
Yeah.
Oh.
This is the elimination reaction. This Kaiser. Huh?